Now, most of you have heard of AI. Of course, who hasn't? That's what we all hear 24/7 for the past few years. Some of you also have heard of large language models, of machine learning, and all of this amazing news about working with AI-based applications or building AI-based applications. And so one of the most important components of building AI-based applications, be it automation or anything else that you can build that connects to a large language model, you need a way to save or a way to persist that data. Now, the thing about the data that large language models deals with, it's not like normal data. Let's say you have a SQL database, because that is what's used usually when you talk about data. With large language models, you need a special kind of databases. You need what we call vector database. So in this mini course, I'm going to show you what vector databases are, how to create them, and how to use them. So it's a crash course on vector databases. Now, even if you've never heard of what a vector database is, I think it's important that you actually learn about vector databases, because it will allow you to understand exactly how to really leverage the tools that are there when you want to build AI-based applications, which I think it's something that you really need to look into if you haven't already. All right, so without any further ado, let's go ahead and get started. So now we're going to dive deep into vector databases, getting started learning and understanding what vector databases are, but more specifically, we're going to learn what is a vector database, why vector databases, so why are they so important, and why are they being so popular nowadays, and what purpose do they serve. And also we're going to look at the limitations of traditional databases, so we can do some sort of a comparison between traditional databases versus vector databases. So what is a vector database? So here is a full definition of a vector database. So a vector database encodes information as vectors in a multi-dimensional space to perform high-efficient queries based on similarity. Okay, no worries. We're going to dissect that as we go. Main keywords. So we have vector. The next keyword is dimensionality. And then we have similarity search. So these three main keywords are part of the definition of what a vector database is. Now, this may not make a lot of sense right now, but that is the whole point of this course, is to define, understand what vector databases are, how they work, and so forth. What I want you to understand essentially encodes information into numerical values called vectors in a multidimensional space. Multidimensional because you can have not 2D, 3D, and multi-dimensional, so many dimensions that can be put into that space. That way it's easy to perform queries based on similarity. Okay, very loaded, but we're going to go through that. So the first thing we need to do before we move forward here is let's start defining parts of those keywords that relate to a vector database. So the first thing we need to understand here, what is a vector? So in mathematics, a vector is defined as a quantity that has a magnitude and a direction. So usually it's represented as an ordered list of numbers. So these numbers are coordinates of the vector, and each number corresponds to a magnitude in a particular dimension. The keywords here is that we have direction and magnitude. So mathematically, this is how you would see a vector represented. So a V and an arrow at the top to say that we have a vector. So if you look at this here, we have an arrow. So the arrow, we said a vector. As an arrow, it has magnitude and direction. So in this case here, we have a tail. So the beginning of this arrow is a tail, and the head, that is the end of the arrow. Okay, a vector. But the thing here, what makes this a vector is that we have, again, direction. So goes left to right, that is a direction. And then it has a magnitude. So magnitude is just, in this case, the length of this arrow. So that's what a vector is mathematically. So if you think about shooting an arrow from a bow, where you aim and how hard you shoot that arrow, bow and arrow in this case, will tell you what the vector would look like. So if this is 0 where you start at the tail and you keep walking this direction, and you end up at, say, a different place in the playground where the slides are, and the distance between here to here is 10, then that means the direction here is this direction from left to right, or in this case it could be east to west, right? And the magnitude is the distance here, let's say 10 steps. So that would be a good analogy when we talk about vectors, mathematically speaking. So let's look at this analogy here. Imagine that you are at a campground somewhere. So the idea is the campground has different campsite. So you are here. This is campsite 1. If you go from campsite 1 to campsite 2, you have two things going here. Well, first of all, you have to know where you're going. So you have the direction. Direction would be toward camp 2. Now we have a magnitude, which would be, in this case, let's say 3.4 miles. So that is a good analogy for us to understand vectors in a real world. Okay, so the main thing here is that we have direction and we have magnitude. That is what a vector represents, direction and magnitude. So this concept is going to be a very important concept as we continue learning about vector databases, hence vector databases, right? So vector databases, which means databases that hold vectors. But we need to understand what kind of vectors are we actually holding or that are held inside of the actual vector database. And that is what we're going to keep exploring, for instance, why vector databases and understanding the whole mechanics behind. Next. So we now know what a vector is, at least mathematically speaking. We understand that a vector represents direction and magnitude. Now let's go ahead and understand the importance of vector databases. Why do we use vector databases? As you know, we have different kinds of databases. We have relational databases or SQL-based databases, and of course non-relational databases or many other types out there. Now you have to understand something that is very crucial, is that first we need to understand how data shows up in the world. Well, it turns out that more than 80% of data is actually unstructured. What does unstructured data means? Well, it means things like images, audio, PDF files, videos, articles, and texts, and everything else, right? So all of these types of data that are not organized per se, they are unstructured data. So this data also needs to be saved somewhere. Now, at this point, we can actually save all these kinds of data into an actual database that you know, a SQL-based database or relational or non-relational database. But the thing is, if you were to save an image or a PDF file into a database, you will have to actually add tags for each one of those items that represent that image or audio or PDF files and so forth, which makes it really difficult for the traditional querying of that data to be fast and efficient. So the main idea was to figure out a way in which all of these unstructured data, which is 80% or more, so you can imagine that most of the data out there is unstructured in this format, a way for us to be able to save that data in a better way, or in a way that it's easy to access and query and do similarity search and so forth. And so that's why vector databases were invented per se, because they are specifically good, extremely good at working with these types of data. Vector database is actually the only type of database that can handle unstructured data. Now the question here is why? Well, the reason being is because vector databases are able to turn this unstructured data, which is 80% and more, right, in the world, into what we call vectors. So vectors, again, in a sense that we have learned what a vector is, has magnitude and it has direction, is a representation of this unstructured data into vectors, which essentially is just numbers. What happens with vector databases is that they are able to take all of these unstructured data and transform it into numbers. Now, the reason why that this is important, the reason why that it is important to have a vector database, or the reason why vector databases were created, is that now when we transform this data, this unstructured data, into numbers, essentially vectors, it's way easier for algorithms to be able to handle queries that are faster and reliable. And on top of that, we have what we call meaning attached to those vectors, and we're going to get into that. So there are a lot of things that happen in the back end to make this whole transaction, this whole transformation worthwhile. So we still have this question of why are vectors used in a vector database? So this takes us back to that analogy we had earlier at the campground. So let's imagine again, you are at a large campground with lots of different campsites. So each one of these are different campsites. Now the thing here is that each campsite represents a piece of information. For instance, some of them campsites could be near water, near the lake. Some of them could be close to hiking trails, and others are near the campground entrance or parking or fishing, near the lake for fishing. These are small features that are attached to each one of those campgrounds. So each one of these flags, they represent a feature. Each campsite has flags that show its features. So here we can have this fish to say that this is close to the lake where they can go and fish. This also means you're close to the river or a body of water where people can swim. This one here means we're close to the entrance where people can park their cars. This one, we are close to hiking trail and so forth. So now we've attached pieces of features as flags into each one of these campsites. Now, if we were to transform all of this campground into vectors, so in this case, the campground as vector representation of that campground with all these features. So what would happen now is that, so now we still have, of course, this information, all these flags that say this is close to the swimming, the body of water, and then close to the entrance, hiking, and so forth, right? So we have all that. So, but now representing that in form of a vector, because we transform that into numbers, it would look something like this. So this campsite, which means it's close to a hiking trail, would be represented like this. This is just an example. And then this one here, close to the entrance where people can park their cars and then go about their time at the campground, would be represented like this. So now you can see the representation is different because now we're representing to say, okay, this could be close to the lake. This actually should be pointing to something like that. Okay, but you get the idea. And then the trail could be this number here, okay? And fishing, in this case, could be this number. So now a campground or campsite represented as a vector would have those pieces of information which are flags or features for each campsite. Okay, so we're representing now what we see visually here into vectors. So we've vectorized the entire campsite, campground, and its feature for each one of those campsites into vector, into numbers. Each feature, like trail, lake, fishing, as I said here, is its own dimension in the vector. So these are different dimensions of this vector. So we can have many, many different dimensions, as you see here, which means we can add different features to represent that campsite. Now, the beauty here is that whenever you want to find a campsite similar to the one you enjoyed last time, say you want the one that is close to the fishing place or close to the hiking trail, the database can easily help you find other campsites with similar flags, in this case, similar features. But the beauty here is it does much quicker and efficiently because it measures how close other vectors, in this case, campsites, are to your favorite one based on the flags they have. If indeed this represents lake and this represents trail, this represents fishing, so this is just one campsite, for instance, then it would look at, it's easier to look at this number here, say 0.05, and this is 0.053. These two numbers are really similar, which means these two are very similar in distance, which means they are close together. Now, this representation here is a little bit off, but I just want to make a point, but you get the idea, right? Because it's easier to say, okay, this first number here, which represents a lake, it's a flag, it's a feature, right? That's the dimension. And that means then, if we have similar or closer numbers or equal numbers, that means they are most likely similar campsites. Which means next time, if you are searching, the database will be able to find you anything that is similar to these numbers, to this feature here, which means closer to the lake, and then propose or recommend you to go to that campsite. A good representation here, imagine that we have this graph here. So this graph represents different points. So if you look at this graph here, we can see that we have a lot of different words. So these words are, in this case, part of the campsites with their flags. So we have entrance, lake, swimming, fire pit, lake, water, Europe, and so forth. So some of these, of course, are pre-related, others are not. So the idea here is very simple. You can see that lake and water, they're very similar in essence, right? So that means they would have, of course, kind of a similar vector representation of them, right? So you can see 0005, 005, and 00885, maybe not that much, but you can see that at least the first dimension is pretty similar. So let's say these two are related, right? So lake and swimming probably related as well, because we can swim in a lake and so forth. But you can see then it's way easier to search for the best campsite, because in this case, lake and water are semantically similar. Lake and swimming, semantically kind of similar as well. But fire pit and entrance, not really. Fire pit and Europe, not really. So now it's way easier, and this is what vector databases are really good at, is to do this quick search for, in this case, best campsite. It's going to go ahead and look the representation of the vector of each one of those campsites with all those flags, all those features, to find quickly the similarity for the meaning for those two words in this case, which are flags, lake and water, and so forth. So we can see now with vectors, in this case vector databases, we gain a few things. First of all, rapid discovery. So just as you might quickly scan the campground map to find sites with the most fish flags if you want to be near the water, vector databases use also their specialized algorithms to scan through vectors, in this case campsites, and find those that are most closely to match your preferences. So we have in this case what we call rapid discoverability. And we also have what we call efficient organization, because if you look at this, if the campsite, in this case these are data points, are organized efficiently in the database, much like a well-planned campground map, the database can swiftly point out which sites will mostly likely appeal to you based on your past likes. So this analogy shows how vector databases allow for nuanced, feature-based comparisons that go beyond simple yes or no answers and really delve into degrees of similarity and preference. This makes them particularly useful for environments where complex, multidimensional data that needs to be sifted through quickly to find matches or make recommendations. It's much like choosing the best campsite based on a combination of desirable features. So in summary, when we talk about vector databases, they give us a lot. So number one is that we have, as I said, efficient representation of complex data. So now this complex data, this raw, this unstructured data has a dimensionality, which means now the data is being represented in high dimensional space, and has uniformity, which means data can be converted into uniform formats. In this case, numerical vectors, which is way better for quick search, similarity search, and so forth, but also enables us to perform similarity search, as I have explained earlier, which also allows us to leverage machine learning models, because the whole point of having vector databases is to interface with machine learning models, large language models, and so forth. We have a huge optimization in performance and scalability that we gain, because now we have what we call indexing, which allows us to efficiently index our vector databases to have a better way to actually access embeddings and so forth. So we'll talk more about that. We also can handle big data with much ease. And we also gain this improved user experience, because we gain this real-time interaction that can now happen efficiently, because the efficient nature of querying capabilities of vector databases that they have, they enable real-time interaction experience to be better. Because imagine, for instance, if we have a system that gives users recommendations on the fly, then we of course, get even better because of the nature of efficient querying capabilities that come with the vector databases for search results or data analysis outputs. So everything is more efficient, is faster because of the nature of vector databases. In conclusion, vectors are used in vector databases primarily because they are able to transform complex and high-dimensional data into manageable, searchable, and scalable format. That's very important to remember. Vectors are used in vector databases because they convert complex and high-dimensional data into manageable pieces that are easy to search and scalable format. This capability is essential in harnessing the power of big data and artificial intelligence, because this whole thing about vector databases is to feed or is to interact with machine learning, which in turn interacts with artificial intelligence, large language models, and so forth. Vector databases are a cornerstone technology in modern data architecture and applications. So I hope these last few lectures are helping you really internalize, really understanding what vector databases are. Now, I do realize there are a few vocabulary words, really, that may still be a little bit hazy, but no worry, we're going to cover them as we go through this course. I just wanted to give you a strong start understanding of why are vectors used in vector databases and what is a vector database. What are the advantages to using vector databases? So as we know, vector databases are very powerful, and so here are some use cases for vector databases. These databases are extremely powerful for handling complex queries. They are really good for certain use cases. The first one is image retrieval and similarity search, recommendation systems that you can build, natural language processing, in this case NPL, fraud detection, bioinformatics, and many others. Okay, so let's go ahead and look at each one of these. So starting with the image retrieval and similarity search. A good example would be if you have an e-commerce platform. In this case, we can use a vector database for a visual search feature. How would that work? So we would have a customer, and the customer is looking for a certain piece. It could be a top, a hat, or pants, or trousers, depending on where you are tuning in from. And what would happen then, that would be sent to our e-commerce system. And of course, this would use the nearest neighbor algorithm, right, to go and find similar items available for sale, determined, of course, by what the user, customer in this case, had uploaded. Okay, and then, of course, we're going to get results and send those results back to our user. And you can see here how this image retrieval and similarity search could help an e-commerce platform to allow user in real time, in this case, to get results that they want from passing in a photo of certain item they would want to buy, to find similar items available for sale. So an overview would be a customer uploads a photo of a piece of clothing they like, and then the system will go ahead and retrieve similar items available for sale by converting this image into the feature vectors and searching for, in this case, as I said, nearest neighbor in the vector space happen. And then, of course, returning the similar items available for sale. Okay, so the next would be, for instance, a recommendation systems. Let's say we have a music streaming service that we have created. A vector database can use to enhance recommendation system by finding items that are similar to those a user has previously liked, as an example. Imagine that a user has certain habits of listening of certain kinds of songs. So our streaming service here has all of the backend stuff, per se, has the nearest neighbor algorithm, everything set up. It's using a vector database and everything. Okay, so what happens now is that the user will have, of course, certain kinds of musics that they listen to, and so our system in the backend here could learn, or would be able to learn, by their preferences, the user's preferences, so the music kinds that they have liked, they dislike, and things that have listened before, and that is actually going to be aggregated into our streaming service system, which has, of course, all of the back end related to vector databases and everything else there. Okay, and so That would allow, for instance, for a user to always receive recommendations from our system of music that they have listened before, of similar kinds of music that they have listened before, they have liked, and so forth. So anything that they have disliked, for instance, this system wouldn't recommend that. It would only recommend, in this case, things that they have liked before, similar to them, or things that they have listened before. Now remember, all of that, of course, all of this recommendation, all of this information, again, it's been saved as vectors, as embeddings in the system. And of course, all of that is inside of the database, which then this algorithm, nearest neighbor algorithm, can work with the vector database and create those recommendations. Of course, we can use natural language processing here as an example. Imagine that we have a customer support AI that we want to create for a certain business. So use case here would be, we could use a vector database to understand and of course respond to user queries more efficiently. So how would that work? This kind of vector databases will facilitate tasks like semantic search, chatbots, document retrieval by storing, searching text converted into vectors for using certain kinds of models, okay? So the example will be very simple. So we have this customer support AI, in this case, and the user comes in with a query. So customer, in this case, asks a question, and what happens is that the AI will convert that text into a vector and compares it to a database of previously answered questions stored as vectors, okay? And so it finds the closest match, of course, to bring up the answers, which in this case would improve response accuracy and speed. All right, another use case would be fraud detection and bioinformatics. For example, detecting fraudulent activities. So we would use a vector database to quickly compare user behavior patterns and flag anomalies and so forth to detect differences and issues and then send a notification. Another example is compare genetic sequences. So we can use a vector database to compare gene expression profiles from different patients' samples. So these are some of the use cases for vector databases and how those can show up or can be implemented in real-world applications. All right, so now we're going to start building vector databases. This is where we're going to start doing hands-on building vector databases from scratch. Very, very exciting. But before we do that, we need to set up our development environment so that we are ready to go. First thing we need to do here is I'm going to be using VS Code, Visual Studio Code, as a code editor. And so I encourage you to go and install that. If you already have that, of course, that is totally fine. And also you have to have Python set up on your machine and ready to go, as well as having OpenAI account and an API key. These are the things that we need to have set up for you to be able to continue in this course. The thing is, if you already have everything set up, VS Code set up, Python is set up on your machine, that's totally fine. You can just move on to the next lectures. So in the next lecture, I'm going to just show quickly how to get VS Code and also direct you to where you can set up Python as well as create an OpenAI account and get an API key. Okay, the first thing we need to do is to install VS Code, Visual Studio Code, which is the text or code editor that I use and one of the most popular out there. But if you go to Google and say VS Code, as such, you will see most likely the first link here. So click on that. Depending on your machine, if you're on Windows, it's going to show here to download for Windows. Because I'm on Mac, it says here, download Mac Universal. So all you do is just click here and start the downloading process, and then double click or click to then install. So depending on your operating system, you should be able to do that real fast and get going. And the next thing you need to do is, of course, set up Python. Now, I'm not going to go through the entire process, but I'm going to show you here real quick where to go to install Python or to set up Python on your machine, depending on whether you're in Windows or Mac. So let me go back real quick here. So if you just say Python setup, there's a lot of information online on how to do so, as you see here. Okay. So you'll see here it says download Python. So I'm going to click on that. So here you can say download Python 3.12.4. This is as of recording of this video. By the time you watch this video, it may be different. That doesn't really matter as long as you are here. So there's a lot of information about Python here. That's not what we are here for. We just want to be able to install and set up Python. So just follow the things here. So for you, if you are on Windows, I'm going to right click to show. Go ahead and follow these instructions here. It all depends, of course, what kind of Windows you are using. And so you find the installer that confirms to your machine. Okay, so go ahead and double click or click to download the executable file and follow the whole process. The other thing you can do also, once you've done that, you can just click here or hover over documents and go to Python documents. Click here, and this is the Python documents where you're going to have all this information. But what I want you to focus on in the beginning is these Python setup and usage. So you can click here, and this will give you all the information you need related to Python, how to configure it, how to make it work on your machine. So as you can see here, it says Python, using Python on Windows, the full installer, the steps, and you can find, of course, for Mac, using Python on Mac, and go from there. Okay, so there's a lot of information out there to get Python running on your machine. All right, so the next thing you need to do is to have an OpenAI account, because we're going to be using the OpenAI API keys to do certain things as we go along using and creating vector databases. So what you will have to do is just go to products like this if you don't have an account already. So say login, API login. And if you don't have an account, of course, you will end up somewhere like this where you want to go ahead and create an account. So what I usually like to do is just say continue with Google or Microsoft account, or with Apple, whichever you want, or you can just add the email here if you have an account. If not, just go ahead and say sign up, which will then give you this where you can add an email, or again, do continue with Google or Microsoft account or with Apple. Either way, it works. And so once you've signed up and everything is good, this is what you will see. You will see something like this. You either can go to ChatGPT or you go to the API. Okay, so we're going to go to API, click like that, and you will see this. And what you want to do is we're going to go to the API keys, click there, and you can go ahead and create a new API key. Now, one thing to keep in mind is that depending on when you're watching this video, things may look totally different. So what you want to do here is that we're going to go ahead and say create new secret key. And in this case here, you can say owned by you or service account, doesn't really matter. And you give a name. And for my case here, I have this project that I'm testing things out. Doesn't matter. You can create a new project to organize all of your API keys. All right. And so I'm going to just give this all for permissions, and then you add the name for your API key. So let's just say something like my API key. Of course, you give it a better name and just go ahead and say create secret key. So I'm not going to create that because I don't need it. But once you've created that API key, then copy that and save and put it in a very safe place. Don't share with anybody, because then we're going to be using that. And that's about it. All right, so let's start with creating a vector database, but using Chroma. So before we even move forward, we need to understand what is the Chroma database workflow. So this is the Chroma database workflow, an overview at least. Let's dissect what's really happening here. So at the top here, we have this layer, which is the app layer. So this is the application that is obviously using a Chroma database. So the top component here, component layer, the layer, represents the overall application or system that integrates, as I said, with various components to handle queries and generate responses. Now, keep in mind that the whole idea that, of course, we have databases, vector databases, is that we store these documents in a form of embeddings, which are, as you know by now, vectors, which could contain a little bit more information than just the actual vectors. So that is the idea. But the main idea is that this data is usually used with the large language model context, meaning that we take this information, then we pass that through a large language model with the query that we have, and then we get an answer, a result. So that is the whole idea. You don't save data just for the sake of saving. In most cases, you save it so that you are able to retrieve it and do all sorts of things. That is the main layer at the top here. We have queries, the LLM context window, essentially is just the large language model and so forth. Okay, let's just dissect everything. So we said that we have the app layer, which has these components there, queries, the large language model context or context window, I should say, and then we get an answer. Okay, but at the bottom here, we have the actual Chroma DB. So we have documents which are chopped into smaller pieces. Now, this is just an example. We have documents, but it could be different kinds of documents or different kinds of data that is being, unstructured data, I should say. Okay, it's just simpler to use general text documents for this purpose. Then we have these queries here. The queries, what does that represent? Well, the queries will be the user's input queries into the app. So these queries can be in various forms, but typically they are text-based questions or requests. And then we have this gen embedding here. What is this? Well, this step involves generating, of course, embeddings for the queries. Remember that in order for us to be able to interact with a vector database, in this case Chroma or any vector database, right, is that we need to force transform that query, which is just a text or voice or whatever, into an actual embedding, because that is the quote-unquote the format, the language that it's needed for the Chroma database to be able to do the semantic search, similarity, and all that stuff. And at the bottom here, we have, as I said, the Chroma database layer, okay, which stores and manages embeddings. So it contains documents. These are likely the textual data or the information entries stored in Chroma. Each document is associated with an embedding, as you see here. All right. And we have the actual embeddings. These are the vector representations, again, of the documents. So each embedding corresponds, again, to a document, and it represents its content in vector form, which allows for similarity comparisons and retrieval based on vector distances, metrics, and so forth. So exactly what we just talked about. So going up here, we have this LLM context window. What this is the large language model that uses the embeddings that we're getting here to understand the context or intent behind the query. It then processes the embeddings to generate a relevant and coherent answer. Okay, so this might also involve using the embeddings to fetch related information, interpret the query's intent, or even generate new text based on learned patterns. And of course, the answer that comes after all of this is put together, okay, the answer is the result, the final output from the large language model, which is sent back to the user. So this answer is indeed generated based on the large language model's processing of the embeddings and its understanding of the context. Okay, it has to have some context provided by the Chroma database. In summary, here's the flow. Here, process flows. Number one, the user may submit some sort of a query, a question to the app, this layer here, this query. Okay. Number two, the second step, the app is going to generate an embedding for that query using a neural network or a similar model. So essentially, we can use OpenAI embeddings, and we'll see all of that stuff to create that embedding. So the whole idea is that this embedding effectively is going to be transforms the query into format suitable for our Chroma database for processing. Okay, we know this stuff now. Now, the query embedding is either compared with existing embeddings that we have here in the Chroma database to find relevant documents, or directly used to generate the actual answer, which goes through the contextual, the LLM context window. So the relevant embeddings, again, all we're getting here from the query, it's transformed into the actual embedding so that it knows how to communicate and do the search and everything that needs to do inside of our Chroma database. It's all pushed and fed to the large language model, and then it is going to go and process that information within the context window, which generates then the answer. Okay, and then the answer, of course, is returned to the user through the app. So the app then is going to get that answer. So that is an overall idea on how a Chroma database workflow would be seen being used in a production setting. Let's look at the significance of all of this. Well, this setup allows the application, in this case at the top level, to leverage deep learning and vector database technologies to handle natural language queries effectively. Because now we're using embeddings and large language models, the system can understand and process complex queries more accurately than traditional keyword-based search systems, because it enables the app to provide responses that are contextually relevant, very important. These are now contextually relevant and semantically rich, enhancing, therefore, user experience and the quality of interactions within the system. So this is the image, this is the lecture, I should say, you should always come back to understand any database. So we're just using Chroma here in this case, but any vector database, at the end of the day, it needs to interact with the real world, in this case, applications and so forth. That is the idea. And these interactions goes through a large language model. Similarity search happens, and semantic search, everything happens, and that is fed then to the large language model. And then the large language model, because it has its knowledge, will know then how to process that information and spit out or create the actual response, the answer that is needed for the user. That is indeed how this whole thing works. Okay, so I have my Visual Studio open here, so we can get started. So it's empty, I don't have any files or anything. Let's go ahead and right click, say app.py to create that entry point file there. And so before we move forward, if we go to Google and say Chroma DB, this is what you most likely will see. So click on one of these, we can go to Chroma Getting Started. And of course, you're going to see the documentation. So there's a lot of information here, guides and deployment and all these things. Obviously, this is not a Chroma DB course, but it's just a way for me to give you an overview of what can be done using Chroma DB, okay, by creating your own instantiation of Chroma DB. And you can see how to add documents or text into the vector database, in this case Chroma, and the vectorization of everything. Okay, so the first thing you have to do, as I say here, you need to go ahead and install Chroma DB package. So you can go and copy this and come here. I'm going to paste in, says pip install. Now, before I even do that, what I need to do is inside of my folder here, I need to create a virtual environment. So this is really good in Python, so that you have virtual environments that are dedicated to that project, so that you don't install all these different dependencies and packages all over the place. To create a virtual environment, I'm going to say Python 3 and then -m, you can say VNV, and I can give it a name. I'm just going to say VNV. Okay, so this will create a virtual environment here. Now, if you're on Windows, of course, things are a little bit different. In Windows, you say Python or py and then -m and VENV, and you can name it my ENV or whatever it is that you want to name. Okay, so that's how you do it on Windows. Okay, so now that we have our virtual environment here, I'm going to go ahead and say source and go to VNV, bin, and activate my virtual environment, which is good. On Windows, it will be something different, which means you have to go to my ENV, if that is the name you gave, and go to scripts, and then invoke the activate executable. All right, so make sure that the virtual environment is activated. Now, make sure your virtual environment is activated. Okay, so we have our virtual environment. So now it's time for us to go back and install the package. So pip install Chroma DB, I should say. Okay, after a few moments, you should have that installed. Next, you just copy all of that. So we're going to import Chroma DB and the client. I'm just going to paste all of that. So there we go. And for me, I have these squiggly lines. I'm just going to go ahead and make sure that I select the interpreter, which is going to be under my virtual environment as such. All right, just a few things there. Okay, so now we've created our Chroma DB client by calling chromadb.client. If you hover over, it tells you other things you could pass, but that's okay. So next, let's go ahead and create a collection. So I'm going to say collection. First, I'm going to put in a name. So collection name. I'm going to just call this test collection. If we go back to our documentation here, you will see that we can go ahead and say collection, Chroma client create collection. So that's what we will do next. So let me go ahead and do that. But what I will do is I'm going to use a different function, which will allow me to do something a little bit different. So I'm going to say collection and say Chroma get collection or Chroma client, and I'm going to use the get or create collection. So if there's already a collection named test collection on your machine, then it's going to go ahead rewrite everything. So I'm going to pass the collection name as such. Next, let's go ahead and define some text documents so we can see something in action. Now, I already have that. And by the way, you're going to have access to all of this, so no worries. I'm going to paste all of that information here. So this is a dictionary essentially of documents. So we have ID, doc 1, doc 2, doc 3, and then for each document we have the text field, which has some fields, which has some text as you see here. You can say, for instance, query hello world. This is the query that we're going to pass through into our Chroma database, and then the Chroma database is going to be able to do all the things that we've talked about, right? Get that and create a little embedding, which is going to go inside and look for the document that is the most similar. But before we define this query, let's go ahead and add these documents into our collection, because now we have the collection. So essentially it's a table, and we want to be able to add some documents into it. To do so, we are going to use the app. Okay, so how do we do that? So if you go back to our documentation here, it says that we can say collection.add. Now the thing about the .add is that because of the nature of what we're doing here, we're going to be running this many times. It's going to keep adding these documents continuously if we call just the .add method. So there is indeed another method called upsert, which will make sure that even if we rerun everything, it's not going to keep adding the same documents. So it's always important to use that. So because we have different documents here, in this case, we just have 1, 2, 3 documents. I'm going to put that inside of a loop so that we can add those documents manually, or rather through a loop. So I'm going to put a loop here, say for document, let's just call this doc for simplicity. And instead of add a document, let's just say upsert. And as you see, we're passing in the document ID. I'm going to just go ahead and pass the IDs as such. So each time we go, we're pulling in the doc ID, which is going to be doc 1, doc 2, doc 3, and put that in. And then we have the text field, which we then pull the doc text. So doc text and get hello world, how are you today, and so forth. So now we've already defined the query text, which we'll be using. Okay, so now let's go ahead and get the results by running the collection query, by passing this query. So I'm going to say results, and I'm going to use the collection and say dot query. That's the method we are going to get. So all of that, again, we can find here, collection.query, and then we can pass a few parameters here. So we have the query text, so we can pass more than just one text, which is what you want to use usually. Inside here, let's go ahead and pass the query. You can see we have query embeddings and all this stuff, but we're going to go to query text, and we pass the first query. So the first query is going to be the query text. Let's go ahead and just say text real quick here, right? Which is this hello there. We are going to pass the results that we want to see, receive back. So I'm going to say n. You can see n results. That's the field parameter, and we want to bring in 3. We can say 2, 1, 3, and so forth. Let's just start with 3. Okay, so to say now these results, it's going to go ahead and pass the query text, which is the query hello world, or whatever it is that we change here, and then the results we're expecting to receive is going to be 3 results essentially. Okay, so for now, let's go ahead and just print results and see what will happen. So let's go ahead and save this. And we're going to run, let's say Python 3, and then run the app.py. Will take a little bit because it's going to go ahead and do all the things that it needs to do. Got an expected text. Looks like I made a mistake. The argument texts. This has to be documents. Okay, this is another thing we need to be very aware of. This actually has to be a list of documents that we're passing along. If you go back here, you can see the field is documents because we can pass more than one, and then we have the IDs. So this is what we are doing here, except that we are doing this in a loop. Okay, let's go ahead and see. All right, so we can see that we are getting results. All the documents, all of the IDs, so doc 1, doc 2, and 3, and the distances. You can see that we have 0.01 and then another distance, and then we have the actual document. So hello world here, the distance of course is going to be 0, 0. That means this is the most similar result, because if we look at the document 1, hello world, and the query that we're passing is hello world, of course this distance is 0, which means it's the most similar. So the closer to 0 it is, the most similar those two are. All right, and the farther out, of course, these numbers here, the less similar they are. Okay, so this is good. So things are working here. So we're going to dissect a little bit more in the next video so we can perhaps make this a little bit better for us to see. But as you can see, it is indeed working. All right, so we know that things are working because we're getting nice results here. Okay, let's go ahead back to our code. And I want to perhaps put in a for loop so we can print things better. So I'm going to say for IDX, I'm going to say documents. Going to pass enumerate, and then I know this results here is pretty loaded, so I'm going to go ahead and get the actual documents, as you can see there, and then get the first item because it comes in as an array. All right, so in this case here, let's just remove all of that, and I'm going to extract the doc ID by saying documents.id, and then get the first element and passing the IDX, right, our iterator, and let's get a distance because we'll need that, and we get that from documents, get a distance, and then go to this distance list, first item, right, such, and then let's go ahead and just print, and I already have all of that, so I'm just gonna get that information here with code as such. Okay, so what we'll do now is that we're going to loop through these results. As you can see here, we are enumerating them, so we are able to pass this ID X, which is going to be the iterator essentially. So we're going to go and grab the doc ID. So essentially from all of this, we're going to go ahead and get the doc ID, and then we are going to get the documents distances. So you can see we have these distances here, which is indeed a list, which will contain a list containing all of the distances for all 3 items in this case, because we only have 3 documents. And then we just print something to say the query found similar documents and pass here the document. Let's see. That's a document as such. And then we get the ID, the doc ID, and as well the distance. So it's going to be much better for us to take a look at. So let's go ahead and clear and give it another run. Right, so this is not document, this should be results. And results, because we're getting from here. Okay, very good. Let's go ahead and... Okay, so we ran. We know for the query, hello world, found similar documents. We have hello world, an ID document, and the distance is 0.0. That means this is the most similar, which makes sense because if the query is hello world and the document is hello world, then of course that should be the most similar one. Now, of course, we are running in a loop here. So again, for the query hello world, and then we're showing the document number 3, distances is pretty high, so 1.19. The same thing for hello world again. Now is looking at the document that says, how are you today? That is also pretty distant. So you can see that this is a winner, of course, because this says hello world. All right, very good. So if I were to change, of course, this to say something that says, let's see what will happen. Okay, so results are in. It looks like, are you good today? It's way similar, obviously. After the search, it's very close to how are you today? That's why the distance for document 2, which is this one here, it says 0.45, and other ones are above 1 because they're not similar, which means they are more distance from the query. All right. So this works. Now, if I were to say something completely different in my query here, say age of the Earth, let's see what will happen. You can see all of them have very high distances to say that none of them are close to the query. So we have no documents that are close or are similar to the query that we have here. So this age of the Earth cannot be found in any of those documents. All right, so there you go. So this was the very simple example to show you how to create, in this case, a hands-on how to create Chroma DB and how to pass in some dummy data documents here. Okay, and then of course start inserting those documents into the database, and then we define the query and we did some querying. So here we can pass different kind of queries or different texts for query. You're just passing one, that's okay. And we are also passing in the end results. How many results do we want to get? So I could say 1 or 2. If we do that, you'll see that we should only get back 2 results, or 2 documents essentially. And then of course we just looping through to get this nice result that is formatted and everything. All right, so what I want you to do is to think perhaps ways to generate different kinds of texts, just for you to practice and see how you can actually, how to use Chroma DB and get started. So very good start, and I hope this was helpful. I'll see you next. All right, so I hope you enjoyed this course. Let me know what you think, what your thoughts are. If you like this content, I would love to hear from you. Let me know what you think. Let me know what you like about this content, if this is something that you're interested in. And also, I just love to hear from you, always. All right, thank you so much, and I'll see you next time.